I'm Jim. Welcome to my channel. Today we're going to do an experiment where we're going to fly a multicopter in a closed up box. I've got a lid that will close this off. We're going to look to see if the weight of the quadcopter in the box change as those airfoils spool up and start spinning and this lifts up. Okay. There's a scale under this end of the box, and then there's a dowel under that end of the box, so we can measure, well, half the weight of the quadcopter in the box. Okay. I will do the experiment first, and then I'll go over why I think it's significant, and then if you want to do this as part of a science fair project, we'll go over how it was set up and some of the things to look out for. Okay. So the quadcopter's in there. There's some fishing line going up and down, running through straws, hot melt glued to the frame of the quadcopter so that it doesn't move around and bounce off the walls. There's a webcam inside, so we don't have the problem of Schrodinger's quadcopter. Okay. So I've got a camera on the scale over here. Let me lift up the quadcopter by hand so you can get an idea of how much effect the weight of the quadcopter has, and if that's the maximum reduction in weight we should see. Okay. And I will close up the box and let's see what happens. Okay, so we got the quadcopter powered up. I connected the batteries. Whoops. I didn't mean to do that. The other camera's on the scale, so the door is closed, so there shouldn't be any airflow, significant amounts flying in and out. So I'm going to ease on the power here. And if I watch the scale, nothing changing really. It actually went down a couple grams. And we have achieved liftoff. And the scale is bouncing around a little bit. Just, I think, the turbulence and, it's not a real stable thing. Get it up a little bit higher. Yeah, on average, I don't think the weight has changed. Drop it down. Let's spool it up one more time just for the fun of it. Yeah, weight's holding basically constant. Okay, so as you saw when I reached in and lifted the copter, we saw the weight on the scale over on this end change, but when we were flying it, as I spun those airfoils through the air, the weight bobbled around a little bit from the turbulence and things going on in there, but there was no significant change as it lifted off. Okay, so why is this a big deal? You've probably seen pictures like this where someone is trying to explain the lift of an airfoil, and they claim that somehow the flow over the top is faster, which is true, okay, but usually not for the reasons stated. They usually tell us that, well, it's because it's curved on the top and flat on the bottom, cross-section of a venturi, Mr. and Mrs. air molecules have to get to the trailing edge food court at the same time, stuff like that, okay. But given that higher speed, Bernoulli tells us that the pressure has to be lower. And again, that's not wrong. The idea that the pressure and velocity trade off, that is correct. But what is wrong is that we are left with the impression, or sometimes flat out told, that this Bernoulli's equation and this lower pressure and higher velocity somehow has nothing to do with Newtonian mechanics and is independent of the fact that the flow above and below the wing has to get a net deflection downward according to Newton's laws. And sometimes we're even told that, well, Newton explains lift on the bottom because there's bottom bouncing balls of air, and Mr. B explains over the top, and then there's two independent laws of physics, that somehow have nothing to do with each other. Nonsense, okay? If that were accurate, if this picture depicting a low pressure over the top with no net change in the direction of airflow were accurate, then we could get lift without the net acceleration of the air in accordance with Newton's second law, okay? And then as we spun up the airfoils on our quadcopter, the magic Bernoulli low pressure would result in a reduction of the weight of the box, right? But it didn't happen. Now, to be clear, okay, there's nothing wrong with Bernoulli's principle, which is just the conservation of energy applied along a streamline to an ideal fluid. The problem is that when well-intentioned but sadly misinformed individuals pass along half-truths without really taking the time to understand the concepts that they're throwing around, then you get these fairy tales, Newton rules, fairy tales drool, okay? Bernoulli and fluid mechanics in general are solidly rooted in Newtonian mechanics. And the Navier-Stokes equations are basically Newton's second law plus conservation of matter. It's not some mysterious magical thing. The math looks really, really ugly, okay? So, given the fact that the weight didn't change, then I think we can rule out this idea of this magic low pressure. As those airfoils spin, the air is accelerated downward or curved downward, both above and below the airfoil. And as that air gets accelerated down, it hits the bottom of the box, and that applies pressure to the bottom of the box, and that pressure shows up on my scale, and the weight doesn't change, okay? And that's one of the reasons that I have to keep it in the middle, because if it moved over here, the weight would get higher just because the pressure area is moving around, okay? And that's that, okay? Now, if you're looking for science fair ideas, this could be combined with other Bernoullian myths, the idea that blowing over a piece of paper demonstrates Bernoulli's principle. I go into that myth in excruciating detail in another video, link in the description. I also have a video and links to a 3D printed Venturi that you can make and actually demonstrate Bernoulli's principle using the Venturi and a vacuum cleaner, okay? And if you do the math, then you can start picking up what Mr. B is throwing down, right? Okay, so a couple other comments on construction and things. Foam core is cheap. I put it together with blue tape so I can take it apart and just reuse the foam core. If you're doing a science fair, you probably want to hot glue the whole thing so it's transportable, right? These straws are hot melt glued to the frame. The fishing line goes straight up and down. I put some cardboard on the top and bottom, kind of reinforce it so this didn't rip through the foam core. A better idea might be to actually just use music wire because it'll be stiffer than the fishing line, which has some slack in it. One other thing to consider, when you position the quadcopter in the box, you probably want to think about how you connect with the battery and have the connection on the side that you can get to instead of in the back like some idiot who shall remain nameless. That end of the box is sitting on the dowel. This end is sitting on a bit of a stick that's sitting on the scale, so you're seeing half the weight on the scale, but that's okay. If you wanted to do math with actual numbers, like how much does this quadcopter way, you can look at in fact that would be a good thing to do for a science fair. You could look at the actual weight of the quadcopter versus how much the scale changes and show that it's about a factor of 2 so that you're getting a legitimate measurement there. What else? You do want the box closed up, because without the first time I did this some years ago, I think you get a lot of airflow going this way. So what actually happened was that the weight seemed to increase every time I lifted off, which was a weird result. Much better result this time with it closed. Also, the having the scale sticking out one end makes it a lot easier to record the weight, and I get better quality video. That should be it. Okay, so I hope you found this at least entertaining, and if you are using it for a science fair or as part of a science fair project on Bernoulli and lift and things like that, let me know. I'm kind of curious how it worked out for you. And I've got other videos on lift and Bernoulli and circulation and airfoil shapes and all kinds of fun stuff. There'll be a link to a playlist down in the description. Okay? So with that, thanks for tuning in. I hope you found it entertaining, and I'll catch you on the flip side.